We're now going to take a look at covalent bonding, which is the third type of bonding that we need to know for the C2 exam. So we've done ionic bonding, we've done metallic bonding, so we'll have a look at what constitutes covalent bonding now. Right, the first thing to remind us about bonding is the periodic table and how that can be useful to help you deduce what kind of bonding you're dealing with. Like I said on the previous video when we're dealing with ionic and metallic bonding, you must draw the back line into your periodic table. You will not get this red line drawn for you in your periodic table that you get given. You need to draw it in yourself. So what this does is it separates the metals which are on the left and the non-metals which are on the right. But remember, of course, that hydrogen is a non-metal, and you need to be aware of this, especially when you're dealing with covalent bonding. So the rule is, if you have two non-metals, then the bonding will be covalent. And remember that bonding involves electrons from the outermost shell. Now, every single atom is trying to achieve a full outer shell. So if it hasn't got a full outer shell, it will do whatever it can in terms of covalent bonding by sharing electrons to try and achieve a full outer shell. Right, so if we look at the two chlorine atoms on the screen, both of these have got 7 electrons in their outside shell. Now, we know this because they're both in group 7, and if you're in group 7, then that means you've got 7 electrons in your outside shell. Now, the only way that these two atoms can get a full outer shell is if they share an electron from each atom to create a pair of electrons like so. And what happens here is the shared pair of electrons basically is the covalent bond. Now if you look at the two atoms, they've both currently got a full outer shell now, so they're both stable by this sharing of electrons that they have carried out. So, to recap, a covalent bond is a shared pair of electrons, and that's a covalent bond, which we saw from the previous slide, but it can be represented by using either the outside shells, which is the more common way, or by drawing a straight line between two atoms. A straight solid line indicates a covalent bond, it indicates a shared pair of electrons. So in the exam, and when you're asked to draw dot and cross diagrams, you don't have to draw all of the inside shells. You can just draw the outside shells, showing where the electrons are in the outermost shell, and that will be absolutely fine. Right, just to recap. Bonding of ionic nature and covalent nature, we'll just give you a bit of a comparison between the two. Covalent bonding occurs between non-metals, it's a sharing of electrons, and there's no charged particles involved. Ionic bonding will occur between a metal and a non-metal. It will involve the loss or gain of electrons, and it will involve charged particles called ions, which form these electrostatic attractions. Right, okay, so what do we do with the giant covalent or simple covalent idea? Now, if you have decided that the bonding that you've got is covalent, then you need to ask yourself, is it one of these four? Is it diamond, graphite, silicon, or silicon dioxide? If it is, then it's classed as being a giant covalent substance. If it's not one of these, and the question in the exam does not tell you that it's giant covalent, then you must assume that it is a simple molecular or simple covalent substance. Now, AQA, the exam board, say that students need to know these 4 giant covalent structures. However, there are other giant covalent structures out there, and if they tell you in the exam that a certain substance is a giant covalent structure, then you must assume that it's giant covalent and apply all the properties of these 4 to the substance that you're given. However, if you are not told it's giant covalent and it's not one of these 4, for example, water, H2O, it's covalent because it's got 2 non-metals joined together, then it's not one of these 4, so it must be a simple covalent substance. And it's about working out the difference between the two. Right, we're starting with simple covalent substances, and we're going to go through these in detail. So the first thing is If we have a look at hydrogen in this particular example, we can see that the two hydrogen atoms have both got one electron in their outside shell. Now hydrogen is happy and is full if it's got one electron added to it. So basically if it's got two electrons in its outside shell, then it's got a full outer shell, because remember the first shell only holds two electrons. So by sharing one electron from each atom, the hydrogen is now stable because it's got a full outer shell. And we can represent that it's a covalent bond, and essentially that hydrogen is now completely stable because of that. Right, now the second type of example we've already looked at is the chlorine. This is simple, the two atoms will share that outermost electron. It's a single covalent bond, fairly straightforward. Oxygen, which is slightly trickier, will have to share two electrons. Now the problem with oxygen, if we just go back, we can see that the oxygen has got 6 electrons in its outside shell. So it's not full, it needs another 2. Now what happens is this oxygen will only be able to get 2 electrons if it offers 2 of its own up for sharing. So whatever one atom offers, the other atom will match it. So because the oxygen needs 2 electrons, it's going to offer to share 2 of its own, and in the hope that the other oxygen will provide 2 of its electrons, which it does. And that's why we get the shared 4 shared electrons, which is a double bond, and that's represented by 2 lines. Now the final example is with nitrogen. Now if you take a look at nitrogen, it's got 5 electrons in its outside shell, and it's obviously 3 electrons away from being filled. So in order to get that 3 electrons, the nitrogen is going to have to donate 3 of its own to the shared area, in the hope that the other nitrogen will donate 3 of his own. And what that results in is you've got 6 electrons that get shared. And that results in a triple bond, which is represented by 3 lines. So there's multiple bonding is just something to be aware of, certainly with things like oxygen and nitrogen. Again, you can have covalent bonds between different elements. So in this case here, the hydrogen, we know it needs 1 electron to be stable, and we've dealt with chlorine from previous examples, that needs 1 electron as well. So what happens is they will share, and in this scenario the hydrogen now has got 2 in its outside shell, it's happy, it's stable, and the chlorine has got now 8, having shared with the hydrogen. And as a result, the covalent bond is formed and we've got 2 stable atoms. Right, the other tricky example is water. Now, water is one of the dot cross diagrams that you need to be able to draw in the exam. You can see that the oxygen has got its 6 crosses for the 6 electrons of its own, but it's sharing 1 of its electrons with this hydrogen, and the hydrogen's given 1 of its electrons to give the covalent bond. And then the oxygen has shared another of its electrons with this hydrogen. So now if you count the number of electrons around the oxygen, you can see there are 8, so it's stable. The hydrogen has only got 2, but remember the first shell only holds 2, so the hydrogen is now stable as well. That gives the formula H2O. Now ammonia, slightly trickier. Again, if you look carefully at this, the nitrogen has got 5 electrons in its outside shell. How would I know this? Well, on the periodic table it's in group 5, and if we look carefully, it is sharing 1 of its electrons with this hydrogen, 1 with this hydrogen at the bottom, and then 1 with the hydrogen on the left hand side. And as a result of that, the hydrogens have donated 1 of theirs to the shared area as well. So the nitrogen has achieved the 3 electrons that it needs by offering out 3 of its own electrons into shared areas. Because remember, atoms will only share the same number of electrons that other atoms are willing to share with them. So in this case, we'd represent this as N with 3 lines to represent 3 covalent bonds. And again, a covalent bond is a shared pair of electrons, and these are all single covalent bonds. Right, the final example is methane. Now methane is again one of the structures that you need to be able to draw. We know that carbon is in group 4, and we know that that means it's got 4 electrons in its outside shell. It's 4 electrons away from being filled, so it has to make 4 covalent bonds in order to get its full outer shell. Because of the 4 crosses that the carbon sort of has, it offers each of those crosses to each of the 4 hydrogens, and the hydrogen provides one of its electrons. And now if you count up, you've got 8 electrons around the carbon, 2 electrons around the hydrogen, and all of these atoms are stable. Now in the exam, a good little check that you can do to make sure that you've drawn a dot cross diagram correctly is, number 1, do all of your atoms have full outer shells? If it's hydrogen, it will be full with 2. If it's any other element, it will be filled with 8. Now if you look at this diagram, we can see that all the hydrogens have got 2 electrons and the carbon has got 8, so they're all filled. The second thing you've got to check for is, do the atoms, if you look at their original electrons, have they got the correct number of original electrons? Now we know that hydrogen has 1 electron, and that's the dot there. So it's got 1 of its original electrons there. That hydrogen's got 1 of its original. That hydrogen's got 1, and this hydrogen's got 1. And then the carbon has got its original 4 crosses that it had to start with. So what you've got to be careful of when you draw these dot cross diagrams, you can't create a situation where you've now suddenly got extra crosses. The carbon only has 4 electrons in its outside shell. So when you draw the dot cross diagram, you can't suddenly generate 5 crosses because the carbon doesn't have 5 electrons, it only has 4. So there are 2 checks that you can make. Number 1, are the outer shells filled? Number 2, do the atoms have the correct original number of electrons that they started with? Right, now a tricky example is carbon dioxide, which is a bit of a confusing one because carbon wants to gain 4 electrons and oxygen wants to gain 2. So what happens is the carbon makes a double bond to the left hand side with the oxygen and to the right hand side with the oxygen. Now the carbon has had to do this because we know that carbon, in order to get stability, has got to share all of its electrons. Because remember the rule, whatever the number of electrons you need, that's how many you're going to have to offer into the shared area. So carbon needing 4 has offered 4 of its crosses into the shared area, 2 on each side, and the oxygen has matched it, and as a result the carbon's now got 8 in its outside shell and the oxygen has got 8 as well. So we do the check that we did on the previous slide. Have all of the elements got 8 electrons? The answer is yes, they have, if we count them up. And secondly, do they all have the correct number of original electrons? Well, we know that oxygen is in group 6, so it should have 6 dots, and it has 1, 2, 3, 4, 5, 6 dots. And the other oxygen, 1, 2, 3, 4, 5, 6 dots. The carbon is in group 4, so it should have 4 crosses, 1, 2, 3, 4. So everything's correct. We haven't grown a couple of extra electrons on the way. We've got the same number of electrons, but we've shared them up, and we've created a situation by which all the atoms now have access to 8 electrons. One other thing to note is that because we're sharing 4 electrons, we've got a double bond. Right, this next part is quite important because with simple covalent structures, we said right at the beginning that if a substance is covalent, you've got to ask yourself, is it one of the big 4? Diamond, graphite, silicon and silicon dioxide. They all are giant covalent structures. If it isn't one of them, then we have to assume it is a simple covalent structure. Now there are hundreds upon hundreds of simple covalent structures. All of the molecules we've just looked at are all simple covalent structures. Now the golden rule with simple covalent structures is they have low melting and boiling points because they have weak intermolecular forces between the molecules. It is essential that piece of information, that actual text, is used in the exam, because when the examiner says to you, why does ammonia have a low boiling point, your answer must be there are weak intermolecular forces between the molecules, therefore the melting and boiling point is low. And that is true for every single simple covalent structure. Now last year in the exam, the examiner asked, why does water have a low boiling point? And the answer was because of the weak intermolecular forces between the molecules. This year it will be a different covalent molecule. It won't be water, it will be something else. But you will have to deduce whether it's covalent or not. And then secondly, if it's covalent, you have to decide, is it giant with a high melting point, or is it simple with a low melting point? And if it's simple, the melting point is low, again because of these weak intermolecular forces. Just to reiterate something as well, within a simple covalent structure, you have strong bonds within the molecule, so the atoms are joined by strong covalent bonds there, but between the different molecules you have these weak intermolecular forces, and that is what you're breaking when you boil water or any other simple covalent substance, and that's why these are generally gases and liquids at room temperature. Right, here are a series of true or false questions that I just want you to have a look at. If you just pause the video, have a go at them, and then play the video and we'll reveal the answers. Right, hopefully you've had a chance to do that, and these are your answers for those. So atoms bond so they have full outer shells, or become half full outer shells, sorry, that's false. Covalent bonding occurs between non-metals, true. A single covalent bond is a shared pair of electrons, it's true. Covalent bonds only occur in compounds, that's false. We looked at an element of chlorine which had a covalent bond between the two chlorine atoms. Oxygen molecules contain double bond is true, and most substances are made up of simple covalent molecules and they are solids at room temperature. That's false. Unfortunately, simple covalent molecules generally have low boiling points and melting points, and they are generally liquids and gases at room temperature, remember, because of the weak intermolecular forces between the molecules. Right, now giant covalent structures. These are the 4 that you need to know for AQA. We've said before in the video. Diamond, graphite, silicon and silicon dioxide. Now the examiner is going to want you to know more detail about diamond and graphite, and we'll come on to that in a little while. But for now we're just going to look at the structure of a giant covalent substance. Now this is silicon dioxide, which is present in sand and is a giant covalent structure. Now what you'll notice about this is that it's a continuous network of covalent bonds between the atoms. Now with all of these structures, they always have really high melting boiling points, and that's because you have lots of strong covalent bonds which require large amounts of energy to overcome, and that's why the melting point of all of these giant covalent structures is very high. Now diamond and graphite are unusual, and you'll need to know specific things about these. Now both of these are allotropes. They're allotropes of the element carbon. An allotrope is just a sort of where you have an element that can exist in 2 different forms. Now carbon itself can actually exist in more than 2 different forms, but 2 of the forms that it does exist in are diamond and graphite. So we're going to go into the structures of both of these. Right, we'll start with diamond first. Now the first thing to note about diamond is, of course, it's made up of carbon atoms, and what you'll notice straight away is each carbon makes 4 covalent bonds. That's essential that you know that. And what this creates is a giant macromolecule in which there are very strong covalent bonds between the carbon atoms. So diamond is very hard, has a very high melting point, and it essentially is a very useful and beautiful material. So it's very hard, the hardest natural substance on Earth. It's a very high melting and boiling point. Again, lots of energy is needed to break these strong covalent bonds. And diamond does not conduct electricity. There are no delocalized electrons in diamond, so it is unable to conduct electricity at all. Right, next up is graphite. Now, graphite's main use is in pencils. Now, what you'll notice about graphite straight away is that carbon's making 3 bonds, whereas in diamond it was making 4. So that's the first sort of difference. The second difference is that graphite's arranged in layers. Now, these distinct layers can slide over each other. And what graphite has got, which is extremely unusual for a macromolecule, is it's got weak intermolecular forces between the layers. Now, graphite is the only giant covalent substance with weak intermolecular forces between the layers. It still has a high melting point, but what the weak intermolecular forces do is they allow the layers to slide over each other, which gives rise to certain properties which we'll look at in a minute. The other thing to note about diamond and graphite is, of course, they're both made of carbon atoms, they're both giant covalent macromolecules with high melting points, but their structures are arranged in such a way that we have very, very different properties in terms of electrical conductivity and the hardness of the substance. So we're looking at graphite now. The graphite is soft and slippery because the layers can slide over each other easily, and this is because of the weak forces of attraction between the layers, and that's why graphite is used as a lubricant in industry and industrial machinery. And it can withstand high temperatures, so it's pretty good for machines that are going to get very, very warm. The second thing is that graphite is a good conductor. Now, you'll recall me saying earlier on that in graphite each carbon atom makes 3 covalent bonds. Now, we spoke earlier in the video about carbon being in group 4. It's got 4 electrons in its outside shell. Well, in this case, we've only got 3 of those electrons being used in bonds. So that means 1 electron is spare, and that electron that's spare becomes delocalized and is allowed to move through the structure. And that is why the graphite is able to conduct electricity, because of these delocalized electrons. We don't get that in diamond because all of the 4 electrons are involved in covalent bonds. Right, the other structure of carbon that we mentioned, I did say there were more than 2, is a fullerene. Now, fullerenes are very unusual. They're simple covalent structures, and their formulas range from C60 to C70 to C80, and they're basically just football molecules. They actually look like footballs, and the carbons inside them are joined together, and these are quite useful in terms of their nanoparticle properties. Now, if you look on the other video, we talk about the uses of nanoparticles, but fullerenes are an example of one of the allotropes of carbon that can be used in nanotechnology. But these are simple covalent structures, so they have low melting and boiling points because of the weak intermolecular forces between the molecules. Right, comparing bonding now. We've done all of the types of bonding, and we're going to look at some of the different structures now. So starting with chlorine, the first thing I've got to do is I've got to decide what kind of bonding it's got. Well, I look on my periodic table and I realise there's 2 non-metals. So straight away I think, right, this is covalent. The next thing I ask myself is it giant or simple? Well, because it's not one of the big 4, it's simple. Therefore, we would say it has a simple structure, and it's got a single bond, it's an element, it's diatomic, and it's a molecule. Okay, I wouldn't use the word giant. It's not a compound because that means you've got 2 different elements, which we haven't got. Allotropes, it's not an allotrope, and it's not got a double or triple bond. Like diamond, again, we know it's covalent. Is it one of the big 4? Yes, so it's immediately giant. Is it an element? Well, yes, because there's only carbon present. Is it a compound? No. Allotrope? Yes. Double bond? No. Triple bond? No. Single bond? Yes. Now, the word molecule, you cannot use that word when you're describing something that is a giant covalent structure. The correct phrase is not molecule, it's macromolecule. If you use the word molecule, you'd be penalised in the exam. Right, oxygen, again, simple structure, simple covalent element. It's got a double bond because there are 4 electrons being shared, and diatomic because there's 2 atoms joined together, and it's a molecule because it's simple covalent. We know that because oxygen is a non-metal, 2 non-metals means covalent bonding. We know it's not giant because it's not one of the big 4, so therefore it's simple. And it hasn't told us this on the slide, but I'd be guessing oxygen has a low melting and boiling point. Right, graphite next. Giant covalent structure, it's one of the big 4. Is it an element? Yes, only contains carbon. Is it an allotrope? Yes. Double bond? No. Triple bond? No. Single bond? Yes. So graphite, it's well worth learning all the properties of graphite. It pretty much comes up on every exam paper. There will be something about diamond and graphite, and if you're aware of all the properties, then you'll be able to answer all the questions. And water, H2O, again covalent. Is it giant? Well, no, because it's not one of the big 4. It's got a simple structure. Is it an element? No, because there's 2 different elements joined together, so it's a compound. It's not an allotrope. It's not got double bonds or triple bonds, they're single bonds because there are 2 electrons being shared, so that's a single bond. Is it diatomic? Well, diatomic means it's made of just 2 atoms. Well, no, because there are 3 atoms here, so it's not diatomic. Is it a molecule? Yes. Okay, because it's a simple structure. If it's a simple structure, it will always be a molecule. And finally, Buckminster fullerene. This is a simple structure, simple covalent, and it has alternate double and single bonds. It would have a low melting and boiling point because it's a simple covalent structure, and it's also one of the allotropes of carbon. And the most important thing is it's used in nanoscience, which is quite important in sort of research and developments looking at health and how nanoscience can be used, and that's discussed in detail in another video. Right, last but not least, we're going to look at some structures. So water, simple or giant covalent, simple. Graphite, giant covalent, it's one of the big 4. Bromine, it's 2 Brs, they're both non-metals, therefore it's covalent. Is it one of the big 4? No, so it's simple. Is bromine going to have a high melting point? No, it's not. It's going to have a very low melting point because it's going to have weak intermolecular forces between the molecules. And then finally, last but not least, ethane. Well, if we look carefully, it's carbon joined to hydrogen, both non-metals, therefore it's covalent bonding. Is it one of the big 4? No, so it must be simple. So without even looking up the data, I know that the boiling and melting point of ethane is going to be low because I know it's simple covalent, it's going to have weak intermolecular forces between the molecules, so I know the melting point is going to be low, and that's why it's a gas at room temperature. Right, just a final review of bonding now. So we've got all of the types of bonding that we've looked at in both videos. We've got ionic, giant covalent, and metallic. Now, ionic bonding, we know the bonding's strong, the melting point's high. Giant covalent, melting point's high, covalent bonds are strong. And metallic structures, the metallic bonds are strong, they have high melting points. So the only things in chemistry that have low melting points is anything that is covalent and simple. So you've worked out that it's covalent and you've deduced that it's one of the simple structures because it's not diamond, graphite, silicon or silicon dioxide. So if it's a simple covalent structure, it's going to have a low melting and boiling point because it's got, again, we've said it 1,000 times, it's weak intermolecular forces between the molecules. There will be a question on your exam paper where they will throw a structure at you, you'll deduce the bonding, and then you've got to decide, is it giant or simple? If it is simple, it will always have a low melting and boiling point because of them very, very simple reasons, the weak intermolecular forces between those molecules. Don't get caught out by that. You must be aware of that. So basically polymers are made by joining together alkenes, and the alkenes that you join together are called monomers. So as you can see in this case, the monomer that I'm using is ethene, and the polymer that we get therefore is polyethene as a result of that. Now you can go through very, very quickly and watch, but essentially the double bond breaks and lots of these ethene molecules will join together, and that will result in polyethene, which is essentially a really, really long molecule with lots and lots of ethenes joined together. And that is polyethene essentially. Now what we're concerned about is that there are different types of polymers. So on the screen now we've got another polymer called polyvinyl chloride, and it's similar to polyethene except you've got a chlorine instead of a hydrogen on the carbon on the end. Now with these different polymers you get different properties, and we're now going to discuss some of those properties in a little bit of detail. So the first thing is the types of polyethene. There's two types of polyethene that you need to know for the exam. The first one is low density polyethene. Now if you look at the top, the low density polyethene is because all of the polymer chains are branched, and that means that they can't fit very closely together, and as a result of that we get low density polyethene, which is basically used for plastic bags and is not as strong. It's quite soft and light. The second type of polyethene is high density polyethene. Now in high density the chains have no branches on them, they're all nice and straight, and as a result of that they can fit very, very close together to give a high density plastic. And this gives a very rigid structure which is harder to melt, and this is used in things like plastic bins. So you've two types of polyethene, low density and high density. Both have different structures and both have different uses, and you need to know both. The second thing about plastics is that you need to know the difference between thermosoftening and thermosetting plastics. Now on the screen here we've got an example of a thermosoftening polymer. Now a thermosoftening polymer will have weak intermolecular forces between the chains, and this is indicated by the dashed lines. And these polymers, if you heat them up, they can be easily reshaped, and they have a low melting point, and as a result of this the polymers can be shaped and moulded into whatever sort of shape you want, and they can be remoulded many times. And as a result of this is because of the weak intermolecular forces between the polymer chains. Right, the second type of plastic you need to know is a thermosetting plastic. Now in these types of plastics you cannot reheat them and shape them. Once they've taken their set shape they can't then be remelted down and heated up and remoulded into different shapes. And the reason for this is because between the different polymer chains you've got these solid lines which indicate covalent bonds. Now these strong covalent bonds, otherwise known as crosslinks, hold the polymer chains firmly in place. So there's absolutely no way that these polymers can be stretched. They have a high melting point, and once they've set it's very, very difficult then to reshape them. If we do decide to try and heat these, they just basically char, and that means they burn essentially.